This is the video tutorial in which I'll be solving the practice questions suggested for the end of term exam, term 2 exam for grade 12 advanced. I'm gonna begin solving the questions of topic 3.1. Now, this topic, the KPIs included are the ones that you are going to differentiate the types of models, the ball and stick, space filling, and the difference between molecular and structural formulas of a hydrocarbon. We will be also, it will also cover the difference between saturated and unsaturated hydrocarbons and how to identify the general formula and functional groups for alkane, alkene, alkynes. It will also discuss the process, the methods used to separate the components of petroleum, the name of the technique, based on what, and the fractions obtained, their name and their uses. So I'm gonna begin. Hydrocarbons means the compounds made up of hydrogen and carbon. So hydrocarbons can be represented using different type of models, like I can represent it model or, so I have the ball and stick model or the space filling model. Now, as you can see, this is the ball and the stick model where I can see the bonds. It's just the atom represented in form of a ball, and the stick represents the bond. And this one is the space filling model. In this model, we do not see the bonds. We only see the atoms bonded to the other atoms. Like here, I have carbon bonded to 4 hydrogens. I'm going to continue the second one, the molecular formula. The molecular formula, when I say CH4, that's a molecular formula. C5H12, that's a molecular formula. It shows the number of atoms, how much atoms I have in a molecule. Like, for example, here I have 5 carbons, I have 12 hydrogens. Whereas the structural formula, I can see the structures. It shows me how these atoms are bonded and arranged together. So over here, this is not a molecular formula. This is a structural formula. So, moving on. Now in this table, they are differentiated between a general formula, whether the compound is saturated, unsaturated, and then to which family it belongs. Now, since we are studying hydrocarbons, I have the family of alkanes, alkenes, and alkynes. So, what is given here, these are the structural formulas. So the compounds, the 3 compounds given here are represented by their structural formula. When they ask about the general formula, it doesn't mean you count. So there's a difference between a general formula and a molecular formula. I'm gonna split this table. In here, I'm gonna show you how do I write the molecular formula for the 3. And here, I'm gonna show you how do I write the general formula. So, since the hydrocarbon over here, all the bonds between the carbons are single bonds, it means that this is an alkane and it is saturated. Because in the saturated, all carbons will have single covalent bonds. And in between every 2 carbons, there are 2 electrons shared, or 1 pair of electrons. Now, as a molecular formula, I have 1, 2, 3, 4. and 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 hydrogens. This is called molecular formula. The general formula of alkane would be CnH2n plus 2. Again, another question, we can see the structural formula over here. Now, because I see triple bond where 6 electrons are shared between these carbons, or I can say 3 pairs of electrons, this is an unsaturated hydrocarbon, and that is an alkyne. Now, as a molecular formula, I have 2 carbons and 2 hydrogens. But as a general formula, the general formula is CnH2n minus 2. And finally, the double bond that we see, which represents 4 electrons shared between these 2 carbons or 2 pairs of electrons, it shows again an unsaturated hydrocarbon, which belongs to the family of alkene. And the molecular formula is 3 carbons. You have over here 1, 2, 3 carbons, and you have 1, 2, 3, 4, 5, and 6 hydrogens. That's a molecular formula, and the general formula is CnH2n. You need to know that unsaturated carbons are only alkynes and alkenes because they contain either at least 1 double bond or 1 triple bond. And whenever you don't see a double bond or a triple bond, it means you are dealing with a saturated alkane. So again here, as I mentioned, what's the difference between a saturated and an unsaturated hydrocarbon? So the saturated hydrocarbon, I'm going to write it here, the saturated hydrocarbons are the ones having single bonds, single covalent bonds between the carbon atoms. So in general, they are the alkanes, whereas unsaturated hydrocarbons are the ones having there's at least one double bond or one triple bond between carbon atoms. And I mean by this, anytime you see an alkene or an alkyne, it means I have an unsaturated hydrocarbon. Now again, the question here is repeated. What is the general formula and functional group? How do I recognize that what I have is an alkane or alkyne? So for alkanes, the general formula is CnH2n plus 2, and I'll recognize them by seeing only single bonds between the carbons. So the functional group means only single bonds between the carbons. The carbon atoms. Now, alkene, the general formula is CnH2n, whereas alkynes, their general formula is CnH2n minus 2. Now, for the alkenes as a functional group, there's I can see at least one double bond between two carbon atoms. And here I can see at least one triple bond between two carbon atoms. So remember this. Now, moving on, in this topic, we also discussed the process used to separate the petroleum compounds. Now, expect this question to come in the exam. The petroleum is separated by the name of the technique is called fractional distillation. Be careful in the exam. They might confuse you and say simple distillation. That's not the answer. Or fractional separation or fractional filtration. It has to be fractional distillation. Memorize this word. And this technique separates the components of petroleum based on their boiling point differences. So it is based on the boiling points differences of the fractions. Now here's a typical question that you definitely are going to get in the exam. The diagram below shows the separation of petroleum into different fractions. Answer questions A to B. Now here, this is the furnace. This is where the petroleum enters and it is heated and changed into steam. And then it's gonna go into the tower. Now, keep in mind that at the top up of the bottom, I obtain the fractions. So at the top, I'll obtain the fractions with the lowest boiling point at the top. And at the bottom, I obtain the fractions with the highest boiling point. Also, at the top, I will get the shortest carbon chains. At the bottom, we get the longest carbon chains. And that means that at the top, they are gases. Then they become, here we obtain the liquid, and at the bottom we obtain the fractions that are in form of, they turn out to be solids. Okay? Now, for the naming, you need to know the naming. So, the name of the fraction is different than the uses of the fraction. So, X is it is named as refinery gas. It is used for domestic heating, cooking, and camping. Why? Here we obtain the fraction that is called gasoline, or what you know as petrol, and the uses, this is the petrol used for cars. Now here, the name of the fraction is kerosene or paraffin, if you want to call it. And this is the fuel as uses. This is the fuel used for airplanes, or oil for central heating, boilers, etc. W, the name of this fraction is diesel oil or gas oil. And the uses of this fraction, it is used as a diesel fuel for buses, trains, some cars as well. Now, before the last, this fraction is called fuel oil, and it is used, this is the fuel used for ships and industrial heating. And last one, the name of this fraction is bitumen, also known as tar, also known as residue. So tar or residue. Okay, and this fraction is used for road surfacing and covering flat roofs of building. So you need to differentiate between the name of the fraction and the use. Now, The fraction that contains the longest hydrocarbons. The longest hydrocarbons, as I said, would be at the bottom of the tower. Write the physical states, and they mean by physical states any gas, liquid, solids. So only the first one is gas, the one in the middle are the ones that are liquid, and this one, the last one at the bottom, is the solid. So here Z is where's Z? Z is here, it's liquid, and U also is liquid. Now, which fraction is it? X or Z is a gas, and which one is a liquid? X is a gas, and Z again is a liquid. So actually, whatever they ask, Y, Z, W, and U are all liquids. X is gas, V is solid. Now we move on to the uses. Heating oil, I wrote it up at the top as diesel oil or gas oil. So heating oil, also known as diesel oil. And this fraction is used as a fuel for fuel for buses, trains, and some cars as well. Whereas the lubricating oil, what is the lubricating oil? Lubricating oil, also known as fuel oil, and this is the fuel used for ships and industrial heating. So it goes as follow. From the top, the fraction is called refinery gas, used for domestic heating. The second one, gasoline, used as a fuel for cars. Next, kerosene. This is the fuel used for airplanes. Next, diesel oil, or what you know as heating oil. This is the fuel used for buses, trains, lorries. Fuel oil or lubricating oil, this is the fuel used for ships. Last one, bitumen or tar or residue, and it is used to cover the road surfaces. Now, let's move on to topic 3.2. In this subtopic, the KPIs included are the ones related to naming alkanes and naming cycloalkane. There is no drawing in this topic. All you have to know is follow the rules to name the alkane, an aliphatic one or a cyclic alkane. So let's begin. Expecting the question to tell you use IUPAC system. That's the way to know that they want you to name it. So the rule is you need to select the longest, biggest carbon chain. And this longest, biggest carbon chain is made up of 1, 2, 3, 4, 5, and 6 carbons. So if I have a 6 carbon, it's gonna be a hex. And since all the bonds are single, it's gonna be a hexane. Now in this hexane, I have 2 branches. Each branch is made up of 1 carbon. So that's a methyl, and that's another methyl. So I have dimethyl. Now all I have to do now is to know from where I should start counting. If I count from this side, 1, 2, 3, 4, 5, and 6, I'll get a branch on the second and on the fifth. And if I count from the other side, 1, 2, 3, 4, 5, and 6, I'll also get the same result. So it doesn't matter in this example. So I'm gonna write hexane as a main chain, and then I have methyl, actually 2 of them, where on the second and on the fifth. Next, this one has 1 carbon. It's a meth, and since I don't see any double or triple bonds, it's a methane without any branches. Next, Over here, I know that you don't see the bonds, but if there is a double bond or a triple bond, the number of hydrogens will be reduced. So therefore, that's an alkane and all the bonds are single bonds. Now let's count. 1, 2, 3, 4, 5, 6, and 7. 7 is a hept, and since this is an alkane, the name it would be heptane with no branches. Next, this chain, here's the longest chain, and I have a branch over here and a branch over here. The branch is made up of one carbon, so it's going to be methyl. Again, this is another methyl. If I have the branch repeated twice, I would say dimethyl. If I have the branch repeated 3 times, I will say trimethyl. Now I need to count. If I count from this side, 1, 2, 3, 4, and 5. I'll have the branches on the third and on the fourth. But if I count from this side, 1, 2, 3, 4, and 5, the branches would be on the second and on the third. This means you need to try both ways. 2 and 3 are less than 3 and 4. So we're going to go with this side of counting. So 5 carbons means I have a pent. And since this is an alkane, it's going to be pentane. Then I have a branch on the second and a branch on the third. Both of the branches are called methyl. And to point that I have methyl repeated twice, I will say dimethyl. Now moving to the cycloalkanes. Again, use the IUPAC system. The only difference here is I'm going to add the the prefix cyclo before putting the name of the main chain. So first, let's start counting. 1, 2, 3, 4, 5, 6, and 7 carbons. That's a hept. And all the bonds are single, that's a heptane. Now, because I see a ring, that's a cycloheptane. Now, this is a methyl, again another methyl, and again another methyl. Since the methyl is repeated 3 times, I'm gonna say trimethyl. So, trimethyl, cycloheptane. Now, I'm not done. I need to tell you the location of these methyl groups. And here comes the counting. I have to count in a way to give the branches the lowest possible number. So I better start with the branch itself. So if I go this way, 1, 2, 3, 4, 5, 6, and 7, I get the branches on the first, on the fourth, and on the sixth. But if I count from the other side, 1, 2, 3, 4, 5, 6, and 7, I'll get the branches on the 1, but this time on the 3, which is better than 4, and this time on the 5th carbon, which is better than 6. So this is the numbering that I'm gonna go with. 1, 3, 5, trimethyl cyclopentane. Now again, another cyclo. This time, this cycle is made up of 3 carbons, which means I have a cyclopropane. Now again, I have a methyl and another methyl, so that's a dimethyl cyclopropane on the first and on the second. 1, 2, dimethyl cyclopropane. Be careful, in the exam, the marks are distributed. So there is a mark for the ane. There's another mark to identify it as a prop and a cyclo. There's a mark to say that this is a methyl and for giving the correct numbering. Next, what's the IUPAC name of 3 carbons? That's a propane. You need to come to the exam knowing this list. Meth, eth, prop, bute, pent, hex. Now when you reach here hex, it reminds me with 6. And then when it comes to hept, oct, non, and dec, it reminds me with September, October, November, and December. It's just a sequence, one after the other. Which of the following is an example of a branched alkane? If I want to see a branch, I'm going to see numbers. If I want to see branches, I need to see numbers. This one, no numbers in the name, it means it's an unbranched one. So, no number, no branch. No number, no branch. This is the only one. And here's the branch. Usually the branch will take the ending of YL, suffix YL. What type of compound is represented by a cyclohexane? So first of all, that's an alkane. That's an alkane made up of 6 carbons and they are making a ring. So a cyclohexane is a cycloalkane. It's not a branched, it's not a straight chain, and definitely it's not an aromatic. Aromatic means benzene. You have to see the benzene in the name and it looks like this. Which of the following compound could be an alkane? Here when they give you numbers, this is where you need to apply the formula CnH2n plus 2 and you're gonna check if this formula is applied or not. So always remember to multiply n by 2 and check if you see the same number, which means this n is 9. So 9 times 2, that's an 18. It means this follows the formula CnH2n alkene. Now, here's n. 7 times 2, that's a 14. But I see here a 16. It means they added 2. So this one follows the formula CnH2n, that's an alkane. N is 10. 10 times 2, a 20. And I see 20. So they applied this formula, they did not add. That's an alkene. Again, N is 4. 4 times 2, that's an 8. But here it's written 6. It means they subtracted 2. So this one is following the formula CnH2n minus 2 and it is an alkyne. So the right answer is B. Moving on to subtopic 3.3. In this subtopic, you need to know how to name an alkene and how to draw an alkene. You also need to name an alkyne and draw the structure of alkyne. So let's begin. The first question says, which of the following is an alkene? So let's first recognize the alkene. That's an ane, suffix ane, that's an alkane. Anyway, there are 2 numbers. I don't know what for. It's so wrong because these 2 numbers means I need to see branches and it's not written. Also here, I have 2 numbers. Okay, one number could be for the location of the ene, but the other number is for what? So that's a mistake. Now we're left out with butene. Is it 3 or 1 butene? Whenever I have an alkene, the location of the double bond needs to be mentioned because you need to tell me, because this double bond could be here or could be at the first. Okay? Now, which one is the correct answer? D is the correct answer. Why not B? It is at the first carbon, the ene. The priority in naming an alkene is to count from the side that is closer to the double bond, which means here I see the double bond on this side, so that's 1, 2, 3, and 4 carbons. So that's a butene on the first carbon. You cannot count from this side and say 1, 2, and 3 and tell me 3 butene. That is wrong. Name the alkene shown below. Again, we need to select the main longest carbon chain, including the double bond. Okay, So let's first put the name of this. 1, 2, 3. I'm gonna put the numbers as well. The side that is closer to the double bond is from the left. My advice to you, always write the number inside the carbon itself, because I don't want you to miss a carbon while counting. So I have here 7 carbons. So this is gonna be a hept. Hept-ene, because I see a double bond. So when you say ene, you've got to tell me where is it located, this ene. It's on the second carbon. So I have 2 heptene. Also on this heptene, on carbon number 4 and carbon number 6, I have the methyl repeated twice. So it's 4 and 6 dimethyl, because it's repeated twice. Next, you are given a branched alkene that contains 1 double bond and 2 alkyl groups. Alkyl groups means branches or carbons, carbon atoms, alkyl, branch from the YL. Okay, so let's look at it. That's a C, another C. That's my longest main chain. But I can see over here a double bond. So I better start counting from this side. 1, 2, 3, 4, 5, 6, and 7 carbons. And I have 1 branch and another branch. So it says 2 alkyl groups, means 2 branches or 2 substituents. That's what it is called. 2 substituents group. So the longest continuous, fill in the blank. So the longest continuous carbon chain, including the double bond, has 7 carbons. The name of this parent chain in this case is going to be hept-ene, because it has a double bond. Where exactly? On the second carbon. Now, how many substituents? Remember, it's called branches, it's called substituents, it's called alkyl, yani carbons. So I have 2 branches, each one is called methyl. Now, the final name, if I want to put the pieces together, this is going to be 4 and 6 dimethyl and 2 heptene. Next, now drawing, naming and drawing. So let's name this one. What is the main chain? Many students will think that this is the main chain, but that's wrong, because the main chain is the longest possible carbon chain, including the triple bond. So I have 1, 2, 3, and 4. As I told you, write the number inside the carbons. If I have 4, it means it's a but. Since I have a triple bond, it's a butene. Where exactly? On the first carbon. 5-methyl 3-heptene. Let's first understand this. I have a double bond. I have 7 carbons, and the double bond is on the third of those 7. And on the 5th carbon, there is a 1 carbon chain. Meth is a 1 carbon. So let's draw 7 carbons over here. 1, 2, 3, 4, 5, 6, and 7. Now you have, I did this one. I have a double bond on the third. 1, 2, 3. So here's the third. I'm gonna put a double bond. I'm done with this. Now I have on the 5th, 4, 5. Here's the 5. I have 1 carbon. That's a 1 carbon. Once you are done, now you move on to drawing the hydrogens. The biggest mistake that the students will do is they draw the hydrogens before they finish. You have to keep the hydrogens till the end. there will be a mark for having the correct number of hydrogens. For here, every carbon is able to have 4 bonds. So 1, 2, 3, and that's the fourth. So only 1 hydrogen it will get. Same thing here. But for this one, for this carbon, 1, 2, it's going to get 2 hydrogens, and so on. So carbon needs to have 4 lines around it. Now, X, Y, and Z. I can see that there's an alkyne, alkene, alkane. Or the bonds between the carbons are single. Or that's the saturated one, and these are the unsaturated ones. So the question says, choose from compound X, Y, and Z the alkene and the alkyne. So X is the alkyne and Y is the alkene. Which of the compound represents the following formula? The black is the carbon, the white is the hydrogen. I have C2H2, that's X. I have C2H4, that's Y. I have C2, 1, 2, 3, 4, 5, and 6. That's it. Now, again, naming alkenes. The main chain in this one. Again, do not start from the middle of the chain. Take one side and slide till the end. Here's a branch, and the main chain is made up of 4 carbons. 1, 2, 3, and 4. I count from the side that is closer to the double bond, and why not also closer to the branch? So I better number it from this side, because if I number from here, the double bond is going to be on the second. If I start numbering from here, I'll show you. 1, 2. I'll get the double bond on the 2, but I get the branch on the 3. So since the other one will also give me the double bond on the 2, so why not also to lower the number of the branch? So 4 carbons means I have a bute. Since I have a double bond, it means I have ene. Where is this ene located? It's on the second carbon. So 2-butene. And I have a branch called methyl, again on the second carbon. 2-methyl, 2-butene. Now, let's first understand the name. Ene, it means I have a double bond between 2 carbons. Oct, it means I have 8 carbons. And the one here, it's telling me that this double bond is on the first carbon. You have 8 carbons. Only the first is holding the double bond. And then on the second carbon and on the fourth carbon, I have 2 branches, 2 numbers, 2 branches. Each branch, so 2 branches. Each branch is made up of 1 carbon. So let's begin and draw it. Oct means 8. 1, 2, 3, 4, 5, 6, 7, and 8. Now, again, leave the hydrogens till the end. I have a double bond on the first. I can put it here or I can put it here. It doesn't matter. On the second and on the fourth, 1, 2, 3, 4. So that's the 4. I have 1 carbon. So 1 carbon here and 1 carbon here. Of course, you can put the branch from top. It's not different. It's the same. Now, let's move on to the hydrogens. As I said, the carbon must have 4 bonds. This carbon. 1, 2, 3, and 4. It's done. It cannot take any more hydrogens. And this one, 1, 2, 3, and 4. So these are the correct number of hydrogens. Be careful not to miss any hydrogen or else you lose marks. Next, what is the main chain? It's definitely not this one. You have to start from one side and slide till the end, like this or like that. It doesn't matter. So, I have this and I have a branch. This time, the branch is made up of 2 carbons. It means it's not meth, it's an ethyl. Now I'm gonna start counting from this side. 1, 2, 3, 4. I have 4 carbons, it means it's a bute. And I have a double bond, it means I have an ene. Where? It's on the first carbon. So 1 butene. And on the second, I have a branch called ethyl. So 2 ethyl, 1 butene. Draw the structure of 2,2-dimethyl 3-hexyne. Let's start understanding the name. Ine means I have a triple bond. Hex means I have 6 carbons, and my triple bond is located on the third carbon. Now, on the second and on the second as well, I have twice repeated the methyl. Methyl is a 1 carbon branch. So this 1 carbon branch, I will see it twice. So let's start. 1, 2, 3, 4, 5, and 6. I'm done with this. I have a triple bond on the third. That's the third. Here's a triple bond. And I have on the second and on the second, on the second and on the second, I have 1 carbon. Now I'm done. All I need to do is put the hydrogens. So I'm going to change the color and put the hydrogens. This carbon, no more hydrogens because 1, 2, 3, and 4 bonds. Also this one, 1, 2, 3, and 4. Saturated. Enough. It cannot, unsaturated. It cannot take any more hydrogens. Now this carbon, 1, 2, 3, and 4. It can't take any more hydrogens. This carbon, 1, 2, 3, and 4. This carbon, 1, 2, 3, and 4. Moving on to subtopic 3.4. In this topic, we discuss the isomers. Isomers are compounds having the same molecular formula, but they're not the same. Their arrangement, their structure, or their name, their properties are different. But the only common thing between them is their molecular formula is the same. So, the first question here, it's asking to compare between structural and geometric isomers. So, it means we have 2 types of isomers. So, structural isomers would be what? So, these are isomers of compounds, isomers of compounds having the same molecular formula, but the arrangement, their structure is different. And I will explain what do I mean by their structure is different. So for example, if I have 4 carbons, so these are 4 carbons, CH3, CH2, CH2, CH3. So the molecular formula of this compound is C4H10. Now this carbon, this compound, I can draw it in a different way. So the structure is different here. The arrangement of carbon atoms together is different. So here, this one is a methyl, 2-methyl propane, whereas this one is simply butane. Therefore, 2-methyl propane and butane are called structural isomers because the arrangement or the way their carbon atoms are bonded is different, but both of them, they have the same molecular formula. That's for structural isomers. Now, in geometric isomers. To have geometric isomers, we need to have a double bond. And then we look at the arrangement of the groups around the double bond in space would be different. So these are isomers, different arrangements. So different arrangements of carbon groups around the double bond. So for geometric isomers, to talk about geometric isomers, you need a double bond. So for example, if I have C double bond C, you need to look at the groups around this double bond. So let's take the first example. That's a hydrogen, that's a CH3, that's a CH2, CH3, and that is a hydrogen. Now, this is compound A. And let me draw compound A in a different form. So again, these are the groups around the C double bond C. If this group, I wrote it up in here, and I didn't do a change in the other one, I would say A and B are geometric isomers because the arrangements around the double bond are different. And more specifically, this is a trans and this is cis. So in order to have a geometric isomers, you first need a double bond, and then you need to examine the groups around the double bond. If the groups are arranged in a different way, showing cis and trans, then these two compounds are geometric isomers. If not, then they are not geometric isomers. Like for example, if I have two carbons like that, I have C and I have Cl, I have H, I have Cl, H and H. This one is not a trans, and these two are not geometric isomers. Even if I draw it in this way, these compounds are exactly the same. These are not isomers. Why? Because there is no double bond over here. There's no double bond here. To have them as geometric isomers, you need to have a double bond. And in this case, one hydrogen has to go like that. These are geometric isomers, trans and cis. You will see more examples as I move on in this revision sheet. Which of the following best describes the relation between the three compounds? If I look at these three compounds, are they structural isomers or geometric isomers? First of all, let's check if they are isomers in the first place. So 1, 2, 3, 4, and 5. Always count the carbons and the hydrogens. 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11, and 12 hydrogens. Now looking at this one, 1, 2, 3, 4, and 5 carbons. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 hydrogens. So pentane and 2-methylbutane, so far, these are two compounds. They have the same molecular formula, but they're named differently. One is pentane, one is 2-methylbutane. Their boiling point is different. So far, these two are isomers. Now let's check the third. 3, 4, and 5 carbons. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 hydrogens. So these three compounds are isomers. Now, are they structural or are they geometric? Do you see any double bond? Do you see any cis and trans arrangements? No. So these are structural isomers. Now, let's identify the type of isomers below. It could be geometric isomers. It could be structural isomers. It could be not isomers at all, like these are two different compounds, or it could be the same compound drawn or written twice. So let's look at this one. I have 4 carbons and I have 10 hydrogens. If you count the hydrogens, you'll find that they are 10. Moving here, I have 3 and that's the 4th carbon, and I have 10 hydrogens as well. So these two compounds are structural isomers because they have the same molecular formula, but their structure is different. The next one, look at the Cl. I have a double bond and I have groups arranged around the double bond, or you can look at the hydrogens. So the arrangement of these groups around the double bond are not the same. That's a trans and that's a cis. So these two are geometric isomers. For more details about isomers, check my video tutorial in which I am explaining structural and geometric isomers in details. Now, what do we do if they gave us a list of names and they are asking us which one are isomers? We don't really need to draw. Let's just understand each one. So A, B, and C. Let's take A. I have 1 butene. So it means I have 4 carbons. I have a double bond, and the double bond is on the first carbon. The second one, I have octene. I have 8 carbons. I have a double bond, and the double bond is on the second carbon. If I look at their molecular formula, this is gonna be C4H8. Remember, the general formula of alkene is CnH2n. Whereas for this one is gonna be C8H16. So these are not isomers at all. These are just simply two different compounds, but it happened to be alkenes. Next, cis-2-butene and trans-2-butene. Now let's look at these isomers. Cis-2-butene, you need to draw it. 1, 2, I have 4 carbons, so you always do 4 carbons like that. So if that's the second and that's the third, because it says on the second I have a butene, I'm gonna draw it in a different way. So butene, I have 4 carbons and I have the double bond on the second. So I'm gonna focus on this double bond over here. This double bond, you'll do like that. I have 1 carbon and I have 1 carbon. I put them next to each other because it says cis-2-butene. This is cis-2-butene. And now trans-2-butene. So again, this same one, I'm gonna draw it in a form of trans. So here's the C double bond C, and I'll put the groups around it. Instead of having the CH3 facing each other, the larger groups, I'm gonna rotate this down. So that is a trans. Now, I wanted to draw these. I know that these are not structural isomers. These are geometric isomers. But I just wanted to show you how to draw them. Now, looking at part C, butane and 2-methylpropane. Let's look at butane and 2-methylpropane. Obviously, I have 2 different names. Now, let's check if they have the same molecular formula. Butane is made up of 4 carbons and it's an alkane. So C4H, remember 2N plus 2. 4 times 2 is 8 plus 2, 10. Now 2-methylpropane. Propane has 3 carbons and methyl is 1 carbon located on the second. So basically we are dealing with 4 carbons and it's an alkane. So CnH2n plus 2. So 4 times 2 plus 2, that's a 10. So these two are structural isomers. Next question. Draw 4 structural isomers of 2-pentene and name each isomer. Now in this KPI, what should you expect in the exam? They are giving you to write possible structural isomers of alkane, alkene, or alkynes, and you're gonna get only up to 6 carbons. So what would be the possible questions? I'm gonna move on here and show you this. The minimum or the smallest isomer they can ask me about is the ones with 4 carbons. So they can either ask me to draw isomers of butane or butene or butyne. Or they can ask me to draw isomers of pentane, pentene, pentyne, or of 6 carbons, hexane, hexene, hexyne, because that's what the KPI says. Now, let me first finish what they are asking me here, the pentene. You need to know that if I have alkenes, alkenes can have isomers between each other and also isomers with the cycloalkane. If I have alkynes to draw, they can have isomers with other alkynes and isomers with cycloalkene. Alkanes can only have isomers with alkanes and nothing cyclic, which means I have more options to draw. So this one I have 2-pentene, I have 5 carbons. Always draw the isomers in the easy way. So you first begin with the maximum chain that you have. If I have pent on the second, let's draw pentene on the first. So here's the first isomer. They want us to do 4. So that's the first one. And I'm gonna name it as 1-pentene. Now, what other possible structures I can have? Instead of having carbon chain of 5, let's make it carbon chain of 4. 1, 2, 3, and 4. And let's have the double bond on the first and the branch before the last. Or I can do a double bond on the fourth, and instead of having the branch here, let's have the branch here. So these are 2 different structures. So you need to have a plan in drawing the isomers. So first you start with the longest chain, and then you start moving the double bond. Once you're done moving the double bond, you can create branches in it, and then branches and moving the double bond. So more and more options. This one is gonna be 3-methyl, 1-butene, whereas this one is 2-methyl, 1-butene. I have an idea. I can have another isomer, and instead of having the double bond over here, let's move it over here. So I'm gonna get a 4th isomer, 1, 2, 3, and 4. The branch is in here, and the double bond is in here. So this one is gonna be 2-methyl, 2-butene. So as you can see, I did 4 isomers. Can I do more? Yes. And if you prefer this way, then go for it instead of drawing these structures. As I said, alkene can have isomers with cycloalkane. You are dealing here with 5 carbons. So the first isomer you can draw a cycle of 5 carbons and call it cyclopentane. Or for example, you can do a cyclobutane with 1 branch. These are again 5 carbons. So methyl cyclobutane. Or for example, you can make a triangle and have 2 branches on it. Again, 2,1,2 dimethyl cyclopropane. Or you can make a cyclopropane, but instead of having 2 methyl on it, why not to have 1 ethyl on it? So that's an ethyl cyclopropane. So here you are making more and more options. Whenever they give you alkene, it's easy. You either go for making different structures or draw cycloalkanes to do it. Okay? Let's take another example. So here I have explained the pentene. Now, moving on to question number 28. Draw any 2 correct structural isomers of butane. So again, if you have alkyne, you can do isomers with alkyne by shifting the triple bond or with cycloalkene. Remember, alkyne isomers with cycloalkene. So bute means I have 4 carbons. So I can have 1, 2, 3, and 4 with triple bond on the first. Or I can have 4 carbons with triple bond on the second. I don't want to repeat and place the triple bond here because that would be the same as this one. So here I have 1 butane. I need to put the hydrogens. Don't forget the hydrogens. 1 butane. And here I have, 2 butane. Can I have more options? Yes. You have 4 carbons. So you can do a cyclobutane, but I said I need to have it a cyclobutene. So here's a double bond. So that's a cyclobutene. Or you can have a cyclopropene and a branch over here. You cannot put the branch here or there. It would be, well, yeah, still. Here's the carbon. Let's look at it. If I have a carbon here, carbon would have 1, 2, 3. Yeah, I can have a branch over here. I can do it like that. So these are 2 other options of isomers for the butane. So that's a methyl cyclopropene. Now this compound is cyclopropene. It's not stable, but it exists. It is, the double bond is between the first and the second. Okay? And the methyl is on the third. So 3 methyl, 1, I forgot the 1 cyclopropene. Or I can start counting from here and say 1 methyl, 1 cyclopropene. Okay, so that's the butane. I gave you the example of the butane. Let me move on more here. In this one, they are asking you to draw the isomers of butane. So when I said in the alkanes, alkanes can only have isomers with alkanes. You cannot have the chance to draw cyclic ones. So if you have 4 carbons, that's the first possible structure. And that's the second possible structure. These are 3 carbons with 1 branch. Now when they give me bute, it means the number of isomers that I can draw is limited. But the more carbons I get, the more possibilities for isomers. This one is butane, and this one is 2-methyl propane. Let me give you the other possible choices that they might ask me. So, if they said to draw butene, what can I do? Isomers for butene. That's an alkene. I can do 4 carbons with double on the first, or 4 carbons with double on the second. So that would be 1 butene and that would be 2 butene. Of course, we should never forget the hydrogens. What else I can have with butene? I can have 3 bonds with double on the first, and look at this carbon. 1, 2, 3, and that's the third bond. So these are 4 carbons. So the name of this one would be 2-methyl 1-propene. What else? Because you have a but 4 carbons, you can do 4 cyclic carbon of cyclobutane. Remember, alkane can only have isomers with alkane. Alkene can have isomers with alkenes and cycloalkanes. Alkynes can have isomers also with alkynes and cycloalkene. Now, since here I have an alkene, I can do cycloalkanes of 4 carbons and I will still get the same molecular formula. Or I can do a cyclopropane with 1 carbon. Go for the easy choices that you can do. So methyl cyclopropane. So that's the butene. I'm done with it. What if they ask me for pentane? Let's do isomers of pentane. So 5 carbons. 1, 2, 3, 4, and 5. That's one possible structure. Or 1, 2, 3, 4, and then 5. It doesn't change if I put the branch over here. It would be again the same as 2-methyl butane. Or I can do 1, 2, 3 with 2 branches. So this one is pentane. This one is 2-methyl butane. And this one is 2,2-dimethyl propane. That's the main chain. So 2,2-dimethyl propane. So if this question comes in the exam, you choose any of those. Pentane. I'm done. Now, what if they ask me to draw the isomers of pentyne? What can I do? If I have pentyne, it means I have 5 carbons and I have a triple bond. Remember, alkyne, they can do isomers with cycloalkene. So I can have 5 carbons cyclic with 1 double bond, or 4 cyclic carbon, 1 double bond, and a branch. And you know what? This branch, you can put it here, or you can put it here with another possible isomer. I'm gonna draw it over here. Or I can do 3 with a double bond and an ethyl, for example. Or 1 methyl here and 1 methyl here. Plenty of choices. طيب, what if I don't want to do cyclic? Can I do isomers for pentyne? Yes, you can do 5 carbons, 1, 2, 3, 4, 5, and have a triple bond on the first. Or you can do 5 carbons and have the triple bond on the second. Or maybe you can do 4 carbons, triple on the first, and a branch over here. So all of these are possible structures for isomers that you can draw for pentyne. Don't forget, if they ask you to name, you need to put the name. So that is for pentyne. Now, I'm left with hexane, hexene, hexyne. What kind of isomers I can do with hexane, hexene, and hexyne? So I'm gonna do here the hexane, the hexene, the hexane. So if I have hexane, I can do 6 carbons straight. So 1, 2, 3, 4, 5, and 6. So the name of this one is hexane. Or I can have 5 carbons with 1 branch on the second carbon. So that is going to be 2-methyl pentane. Of course, don't forget the hydrogens. Or instead of having 2-methyl pentane, why not 3-methyl pentane? Or maybe I don't want to do a pentane. Let's do 4 carbon chains and have branches next to each other. Or let's do 4 carbon chains and have the carbons on the branches on the same carbon. So all of these are possibilities. The more carbons they give you, the easier it gets, because you have more possibilities to think of and to draw. Now, if the question was hexene, it's even easier. So you can start with 6 carbons, 4, 5, and 6, and you can start shifting the location of the double bond and have more isomers. So that's a 1-hexene. Or let's do 2-hexene. So instead of having the double bond on the first, let's have it on the second. 1, 2, 3, 4, 5, and 6. So 3, 1, 1, 2, 2, and 3. So that is going to be 2-hexene. What about doing it on the third? 1, 2, 3, 4, 5, and 6. So let's put the double bond on the third. That's a 3-hexene. Are there other possibilities? Yes, of course. You can go for a smaller chain. What about 5 carbons? 1, 2, 3, 4, and 5 with a double bond on the first and a branch here. Or 5 carbons, double bond on the first, but instead of having the branch on the second carbon, let's put it on the third. Or let's put it on the before the last, and so on. So many options you can do. And hexene, you have 6 carbons. You can think about cyclohexane, or you can think about a cyclopentane with 1 carbon, or a cyclobutane with 2 CH3 branches, or maybe a cyclobutane with CH3 separated by 1 carbon. So many options. So the list will keep on going. So you just think about a way of possible ways to draw the structure. But keep in mind that alkenes, I can also use and draw cycloalkane. And if they ask me to draw isomers of alkynes, I can draw also some isomers of cycloalkene. Now, last one, hexane. So I can do the option just like I did here with the hexene, and I can shift the triple bond. So a triple bond on the first, 3, 4, 5, and 6. Or a triple bond on the second. Or let's do the triple bond on the third. So 1-hexane, 2-hexane, 3-hexane. Of course, you need to put the hydrogens. Never forget to draw the hydrogens. Or in the hexane, I can do a cyclohexene, only 1 double bond you have to do. Or a cyclopentene with a triple bond here. Double bond here and a branch here. Or maybe the branch, let's make it a bit far from the double bond. And so many options. I hope that you get the point of drawing isomers. Now, moving on to the last topic of last subtopic of topic 3, it's about benzene, the aromatic compounds. So the KPIs included in this part covers to describe the structure of benzene and its reactivity, if it's reactive or not, and the resonance, to distinguish between aliphatic and aromatic carbons, and to name the aromatic carbons. So it's pretty direct and simple. So how does benzene look like? Which one is a correct structure of benzene except that is a benzene? That is another way to draw a benzene. Again, I can see a ring of 6 carbons with the 3 alternating double bonds. So that is again a benzene. But this one is not a benzene because it has only 2 double bonds. So to have aromatic compound or to have benzene, you need to have a ring of 6 carbons with 3 double bonds. So it could be like this, or like that, or simply if I want to draw both, I would go for this one. Means that the electrons are rotating inside this benzene ring. Which statement best describes benzene's bonding? It's a cyclohexane ring with, it's not a cyclohexane ring. I don't have an alkane, it's double bonds, I have double bonds. And I don't call it a cyclohexane. I don't even call it a cyclohexane. I call it a benzene ring. So a benzene ring it doesn't react like alkene as also the benzene. So benzene is an aromatic hydrocarbon. You might be wondering why she's saying this is not cyclohex. I know it's a carbon of 6, it's a ring of 6 carbons, but this is a cyclohexane and this is a cyclohexene. This is a cyclodiene. You know, it's a cyclohexadiene, like 2 double bond. But this is not at all a cyclohexene. Not at all. This is benzene. Which of the following is an aromatic hydrocarbon? Again, if I have an aromatic hydrocarbon, it must have the benzene ring, which is represented here by C6H6. That is the benzene ring. So here, it's not a cyclohexane. It's not a hex-1-ene. It's a benzene of C6H6. The benzene molecule is characterized by a ring of delocalized electrons with alternating single and double bonds. What do I mean by delocalized? You see this structure when they draw a circle? What do they actually mean by this circle? It's simply the rotation, or what we call the delocalization of electrons between the double bond. Why do I have a structure like this? It's because the 2 electrons over here, they rotate, those 2. So these 2 electrons over here, they shift location and they move here. And if they moved here on this side, they're going to push the double bond here to go on this one. So this one will have to move over here. And if this double bond is now over here, then this has to go up in here. So we say a ring of delocalized electrons, means moving, changing location. So when we draw this structure, we are referring to this circle that we have 6 electrons, 2 here, 2 here, and 2 here. So a total of 6 electrons rotating inside this ring. Now, how do I distinguish between aliphatic and aromatic hydrocarbons? And how do I name the aromatic? So, aliphatic, it means it has no benzene ring in it. Aromatic, it means it has, I can see a structure of benzene. So, structural characteristics, aromatic compounds, it contains benzene ring. Okay? It could be more than one benzene ring. So it contains at least one benzene ring. I can have 2, 3, 4, whatever. As long as I see at least one, it means that's aromatic. Well, aliphatic, it is it's the alkenes, alkynes, and alkanes. These are the aliphatic. So these are straight carbon chains or branched carbon chains, but no benzene ring in the formula, in the structure. So they have no benzene ring inside them. They do not contain benzene ring. Now, what about the reactivity? In general, hydrocarbons are reactive, and alkane are the least reactive. Alkenes are a bit more reactive. Alkynes are more and more and more reactive. So these are more reactive than aromatic. Aromatic compounds, they are even less reactive than alkanes. So they are less reactive than, they don't react at all, than aromatic, than aliphatic hydrocarbons. Explain how hydrocarbon aromatic differs from aliphatic. Again, I'm gonna say that the aromatic, they contain benzene ring, whereas the aliphatic, they don't have benzene ring. They could be straight chains of carbon or branched chains of carbon. They could be alkane, alkene, alkynes, but no benzene ring. Now, how do I name the compounds that are aromatic? What is the name of the compound in which I have one ethyl group attached to a benzene? So it's simply ethyl benzene. Now, I want to mention here that toluene is a methyl group attached to a benzene ring. And these two are wrong. There is no such name. How do I name these compounds? Give the IUPAC name. So, first, you need to count or number the branches in a way that gives them the lowest possible number. So, if I number this as 1, 2, 3, 4, and 5, I'm gonna get branches on the first, on the third, and on the fifth. Now let's do another way of numbering. I'm gonna use the red color. What if I name 1, 2, 3, 4, 5, and 6? I'm gonna get branches on the first, on the third, and on the fifth. Now the numbering in all directions, it's always ending up with the same numbers, 135, 135. So we move to the next priority, which is how about we give the letter that comes first in the alphabet, the lowest possible number. And I mean by this branch is called a methyl, and this branch is called a methyl, whereas this branch is called an ethyl. In this case, if you have ethyl, E comes before M alphabetically, and I have to start writing it in the compound, because as you know, if you have more than one different branch, you need to start writing the branches in the alphabetical order. So I'm gonna go with this. So one ethyl, and I have on the third and on the fifth two methyl groups, and last you end it with benzene. What about this one? This is a branch of 3 carbons, so that's a propyl. And this is a branch of 2 carbon, that's an ethyl. And that is benzene ring. So how do I name it? My ranges on the first and on the fourth, or on the first and on the fourth. Should I say 4 ethyl or 1 ethyl? Or should I say 1 propyl or 4 propyl? Since the numbers here are the same, we go for the next priority, which is using the alphabetical order. So we better say 1 ethyl, 4 propyl. Always when writing it, be careful to start with the one that comes alphabetically before, and always end with the main chain, which is benzene. More questions to name. I have a propyl and I have another propyl, and this is benzene. Since propyl is repeated twice, I'm gonna say dipropyl benzene. But I need to tell you where are they located. I can see one on the first and one on the third. 1,3-dipropyl benzene. Now, last question in this subtopic 3.5. Name the compound below. That is not just a benzene. That's a benzene with a methyl group. That's not a phenol, because the phenol is like this. You don't have to know it, but it is a benzene with an alcohol group, a hydroxyl group. That is toluene. Toluene is a benzene ring with one methyl group, also called methyl benzene. Hexene is just 6 carbon with a double bond. To answering questions of subtopic 4.1. In this subtopic, you really need to put a lot of effort and memorize the formula and the name of the functional groups, the name of the functional group, the formula, and the family group it belongs to. So let's begin with all the functional groups that you need to know. So OH. So let's start with this one. OH, whenever you see OH, that's a hydroxyl functional group. So OH is a hydroxyl functional group. Now this hydroxyl, whenever I see it, it means I have an alcohol. I'm going to explain the meaning of R by the end of this table. Now ether. Ether is an oxygen atom between 2 carbon chains. So carbon and carbon. Now I'm going to represent it by R and R prime. And the name of the family group of the ether is also ether. So that's easy to remember. Family compound, family group, and functional group of ether, it's the same name, and it's simply an O between two carbons. There is no double bond. Now, the presence of nitrogen atom and there is no double bond, it means I have an amino functional group and it belongs to the family of amines. Remember, amino and amines. Now, aldehyde and ketones. Aldehyde and ketones, they share the same functional group, which is carbonyl. Carbonyl looks like this, C double bond O. Now the difference between aldehyde and ketone is that in the aldehyde, it is the carbon number 1 of the chain. So it's the first in the chain, so it's always followed by a hydrogen, and the rest is a carbon chain. Whereas ketone, the C double bond O comes in the middle of the chain. So there is a carbon from the left, maybe 1 or 2 or 3 carbons, and carbon from the right. I'm going to write it R and R prime because probably the chains are not symmetrical, or I can have, for example, a ketone with one CH3 from this side and CH3, CH2 from the other side. So that's why I wrote R and R prime, because the carbon chains could be different. Now, carboxyl functional group, this belongs to the family of carboxylic acid. Carboxyl, note here that I have a carbonyl and a hydroxyl. So the carboxyl is whenever I have a carbonyl bonded to a hydroxyl group. So let's put again the carbonyl and let's put the hydroxyl. Together, they make a carboxylic acid. Ester. The good thing about ester is the name of the family group is also the same. And also amide, it is the same. Now, ester is a carbonyl group plus oxygen atom. So it's a carbonyl group and then there's an oxygen. So here it continues with a carbon chain, and also from this side it continues with another carbon chain. Amide, I have a carbonyl and a nitrogen atom after. So I have a carbonyl and followed by a nitrogen atom. Now this nitrogen atom could have hydrogens or it could be bonded to carbon chains. Same thing here, it could be bonded to carbon chains. Now, I hope now that you figured out what is R. R is a carbon chain. So instead of writing CO, for example, like this, I can represent it by ROR. Or probably here, it means I have carbons from the left. Here I have carbon and hydrogens bonded from the left and the right. Here I only have a chain of carbon from the left. Here I have on these sides carbon chains. It could be straight, it could be with branches, it could be a cyclic chain, a cyclic alkane. So R represents the alkyl group. The alkyl group, which means carbon chains. Now, one thing I want to point at, alcohol and ether, if the number of carbons of alcohol is equal to the number of carbons in an ether, so if I give you an alcohol and an ether and they both have the same number of carbons, they will have the same molecular formula. So these compounds, if number of carbon is equal, they can form isomers. I'm going to give you an example over here. So for example, I have CH3CH2OH. That's an alcohol. And I also have an ether, methyl ether. If you look at the molecular formula here, it is C2H6O. and also here C2H6O. So alcohol and ether, they can give you questions about them, and you need to check if the number of carbons in both are equal. They will be considered isomers. Same thing for aldehyde and ketone. If in the aldehyde the number of carbons is equal to the given molecule of ketone, also having the same number of carbons, they would form isomers. So let's give you an example of an aldehyde and ketone with the same number of carbons. So let's say I have 3 carbons propanal, that's an aldehyde, and I have 3 carbons propanone, that's a ketone. So the molecular formula in here is C3H6O, and also here C3H6O. So again, I can have isomers. They can give me a question of an ketone and aldehyde, and they can ask me whether they are isomers or not. Same thing for the carboxylic acid and esters. If the number of carbons is equal in both, they could be isomers. And I will give you an example. For example, I have CH3, CH2, COOH. That is a carboxylic acid. Now this carboxylic acid has 3 carbons. Now let me give you an ester with 3 carbons. Here's an ester with the 3 carbons. The molecular formula of this one would be C3H6O2, and the molecular formula in this one is also C3H6O2. So both can be isomers. That's it. The rest, amine and amide, cannot form isomers because amide has oxygen, whereas amine no oxygen in it. Which of the following represents the correct pair of name and formula of the functional group? You must not get confused between the name of the compound and the functional group. So let's see. A carbonyl. A carbonyl is a C double bond O. Since there are no hydrogens on the C, it means a carbonyl could be represented like this, CO or CO, by showing the bonds. So that's the name and that's the formula. This one is correct. Next, carboxyl. Carboxyl is a carbonyl and a hydroxyl. What they are showing me here is an ester. Let me write it in a proper way. So carboxyl is like this, but what they are showing me here is an ester, C double bond O and O. Now, hydrogen is not a functional group that we studied, and this one is hydroxyl. Now, ester, I already mentioned it in B, and this goes for the carboxyl. So the correct combination is A. Which of the following statements are true? Alcohols and ether having the same number of carbons, they have the same molecular formula. Yes, this is correct. But amine and amide, they cannot have the same functional groups. That is not true. Amine, I have nitrogen atom, whereas amide bonded to carbon chain, whereas amide I have carbonyl and a nitrogen atom. So that's the amide and that is the amine. They are both different. Again, which of the following is an amino group? Amino group is the name of the functional group of amines. It means I need a nitrogen. This one is called thiol. Again, this one is a carbonyl and a hydroxyl, which is called carboxyl. And this is a hydroxyl that we see in alcohol. This one we see it in carboxylic acid. This one we see it in thiols. Expect questions like that. You really need to know the name of the functional groups, their form, like how do they look like, and the name of their family group. Again, hydroxyl. Hydroxyl is D. This one is carboxyl. This one is thiol. And guess what? There's a carbon and there's an oxygen and there's a nitrogen. So that is amide. C double bond O, and there is an H2. Which of the following is thiol? That is thiol. Now consider the structure of organic compounds X, Y, and Z. Now let's look, before we start answering the questions, let's look at what we have. That's a benzene ring. So if they ask me if this is an aromatic compound, X is aromatic. Now, always highlight the functional group so that you can pay attention to it. That's a carbonyl and an oxygen. That is the functional group of ester. And here I only have oxygen between carbon chains. That is an ether. So identify the functional group of Y and of Z. Y is ester and Z is ether. So ester and ether. Next, which compound is classified as aromatic? So it must contain benzene ring. So like I said, that is compound X because it has benzene ring. So that is the justification. It has a benzene ring. Next, use the structure of vanilla given below to answer the questions. So let's first look at this functional group. This is the carbonyl. Again, that is a benzene ring. This is hydroxyl. It's okay if they wrote it HO or OH. So that's hydroxyl. And that is a function for ether. Okay? So which letter represents an ether? It's X. What is Y? Y is hydroxyl and Z is carbonyl. Moving on. Name the ring represented by W. W is a benzene ring. Now, which of the following is a functional group of amide? Usually the students, they get confused between amides and amine. Amine is just a carbon with nitrogen. There is no double bond over here. So that is functional group called amino. That is functional group called amide. This one is a carbonyl and hydroxyl, like I told you. So this functional group is carboxyl. This one, we did not learn it. Actually, there is no such thing. Which of the, compare and contrast the alkyl halides and aryl halides. So first of all, to be a halide, the alkane chain must have a halogen, one or more halogen atoms bonded to it, attached to it. What are halogens? A halogen is F, fluorine, chlorine, bromine, and iodine. These are elements of group 17 of the periodic table. Now, what's the difference between alkyl halide and aryl halide? Alkyl halide is the hydrocarbon with halogen bonded to it, with halogen bonded to it. Now, the hydrocarbon must be aliphatic. So you either say the hydrocarbon is aliphatic, or if you find that word hard, it means no benzene ring. So the hydrocarbon must not have benzene ring, only the halogen bonded to it. Now aryl halide is an aromatic hydrocarbon. An aromatic hydrocarbon, it means a carbon with a benzene cycle, benzene ring. So an aromatic hydrocarbon bonded or with a halogen bonded to it, with a halogen bonded to it. So remember this. So for example here, we need to classify them. That is benzene, so it's an aryl halide. I don't see any benzene, but I see the halogen. Look at the halogens, I'm going to highlight them. So in the second one, there is no benzene, so I classify it as alkyl halide. This one, I have a benzene, so it's going to be an aryl, classified as aryl halide. And here, there is no benzene, it's simply an aliphatic hydrocarbon, so it is an alkyl halide. Remember, the word aryl comes from the word aromatic. Now, let's move to the questions of topic 4.2. In this topic, you need to define an alcohol and know how to classify it into primary, secondary, tertiary. You need also to learn to know how to write the IUPAC name of an alcohol or draw it if the IUPAC name is given. And you need to know, you need to explain, to be able to explain the differences in the boiling point of an alkene and alcohol if both have the same number of carbons. And you need to name ethers. You need to define an amine and classify it into primary, secondary, and tertiary, and define the substitution reactions. So let's begin. An organic compound X contain OH. So again, that's a hydroxyl group attached to a straight chain of alkene. The compound would be an alcohol. If I need to answer A, they must tell me that the organic compound X contain a carbonyl attached or bonded to oxygen, so that I can answer A. Or if I need to answer B, they need to tell me that the organic compound X contain oxygen within the carbon chain, O, between carbons. And if I need to answer C, they must say in the question an organic compound containing a carbonyl group bonded to nitrogen atom. So expect any changes in this question, and like this now you can know which choice to answer if the question changed. An alcohol is an organic compound in which something replaces a hydrogen atom and a hydrocarbon. I'm going to show you a hydrocarbon with hydrogens bonded to the carbon. Okay? So here's a hydrogen, here's an alkane. How this alkane becomes an alcohol, I need, for example, to replace this hydrogen that I erased with a hydroxyl group. If I replaced it with a halogen, it's gonna become a haloalkane. If I replaced it with a nitrogen, it's gonna become an amine. Okay? So just that, so that you know the difference. Which of the following is a primary alcohol? Now, primary alcohol, you need to count the hydrogen atoms found on the carbon holding the OH group. So there are here 4 carbons, but which carbon I look at? This one. Here's the OH and this is the carbon holding it. So how many hydrogens on it? 2 hydrogens. It means that is a primary alcohol. Memorize this expression. 2 for 1, 1 for 2. So when you count 2 hydrogens, you will say primary. When you count 1 hydrogen, you will say secondary. When you count no hydrogen, there are no hydrogens, you will say the third option, tertiary. So this one is a primary alcohol. Now let's look at this one. Here's the OH group and here's the carbon holding it. How many hydrogens on this one? 0 hydrogens. So this one is a tertiary. Now, this one is not an alcohol. That's an amine. Now, for amine, we can also classify them by counting the hydrogens, this time on the nitrogen, not the carbon. So we count the hydrogens bonded to N. So to classify the amines, we count how many hydrogen atoms are on nitrogen atom. And again, 2 for 1, 1 for 2, 0, you will say tertiary. So this N has 2 hydrogens. That's a primary amine. Let's continue. Why do alcohol have higher boiling points than alkane with the same number of carbons? Suppose I have CH3, CH2, CH3. That is a propane. And I have CH3, CH2, and CH2OH. That is a propanol. So these are, this is an alcohol and an alkane having the same number of carbons. Usually, the boiling point of the alcohol would be higher simply because, I need to say why. Alcohols are polar while alkanes are non-polar. And this means that alcohols can form strong intermolecular forces between their bonds, while alkane cannot form strong intermolecular forces between their bonds. The one that are their intermolecular forces are weak. So I'm gonna write it here in a clear way. Alcohol are polar, while alkanes are not polar. Therefore, the intermolecular forces between alcohol molecules are strong because alcohol can form hydrogen bonds are strong. Their type is hydrogen bond type. Whereas the intermolecular forces between alkane molecules are weak. What is their type? They are the type of London dispersion forces. So you need to understand something. If I have a liquid and I need to boil it to make it a gas, I need to break the intermolecular forces between the molecules of liquid. I need to make them loose and weak and break in order to turn to gas. So if these intermolecular forces are strong, if they are hydrogen bonds, because hydrogen bonds are known to be strong, therefore breaking those intermolecular forces would require more energy or higher temperature. But if the intermolecular forces between the molecules are weak, I don't need that much of energy. The temperature shouldn't be that high in order to break those forces and make the liquid turn gas. So that is the reason. Alcohols are polar. So alcohols are polar. So they have strong intermolecular forces that are called hydrogen bonds. Alkanes are nonpolar and their intermolecular forces are weak and they are called London dispersion forces. For these reasons, the boiling point of alcohol is always higher than the boiling point of alkane. If this question comes in the exam, you must write it all. Now let's draw. When we are drawing, the first thing I need you to check is the modifier at the end, the suffix ending with the molecule, so that you'll know if you have an alcohol or something else. So here it ends with all. All means you need to attach an OH group. Where exactly? On the first carbon. Now, how many carbons I have? I have 4 carbons. So I'm gonna draw 4 carbons, and on the first one, I'm gonna attach an OH, and I'm done. The rest would be the hydrogen atoms. Now, if the name is 2-butanol, it means this OH group is attached on the second carbon. So here's the first, here's the second, and that's it. You must not forget to draw the hydrogen atoms. Naming ethers. If I want to name ether, I am going to follow the easy way, which is we deal with every side of the oxygen as a branch. So this one, 3 carbons, that is a propyl. And this one is a 1 carbon, that is a methyl. Remember the termination of branches. Now, when I write them, I start with the one that comes first alphabetically. So methyl, propyl, and I end it with ether. Let's move on. Give the name of compound A and give the name of compound B. Again, this is an ether, but this ether is symmetrical. The 2 groups here are both methyl. So you can either say methyl ether or dimethyl ether. Both are accepted. So if I only see methyl, I don't see another name next to it, it means I have a symmetrical ether. It means that the groups around the O are both the same. Now the main chain here is made up of 2 carbons. That's an ethane. Now this functional group is an alcohol, so I have an ethanol. There's no need to say 1 because there are only 2 carbons. Define amine. So which of the following is a secondary amine? Again, as I told you, you need to count the hydrogens on N, not on C, holding OH like the hydroxyl. You need to count the hydrogens on N. I have 2 hydrogens. Remember this expression, 2 for 1, 1 for 2. So I counted 2, that is primary. I counted 1, that is secondary. That's an alcohol, not an amine, and that's an ether, not an amine. Now, define substitution reaction. A substitution means a replacement. So a substitution reaction is a reaction in which an atom, in our case, it's going to be hydrogen atom or halogen, for example, an atom is replaced with another atom or a group of atoms, like a molecule. Okay? So that is basically the meaning of a substitution reaction. Now here, expect in the exam to give you questions probably to complete the equation of a substitution reaction. So here, write the general equation of a substitution reaction, including halogenation of alkane, alkyl halide turning to alcohol, and alkyl halide turning to ammonia. I'm going to give an example for the three of them. So for example, an example 2, substitution halogenation. It is called halogenation. Halogenation, it means I have a halogen. Could be Cl2, F2, Br2, or I2. So I have an alkane. Suppose I have CH2H6, for example. Okay? So I'm going to add to it Cl2. Now Cl2 is 2 Cl atoms bonded together. Now under the effect of heat and UV light, this bond over here will be broken. So this bond breaks and I will have 2Cl broken. So what's going to happen is that any hydrogen from here, let's say this one, any hydrogen atom will be replaced by one of those atoms. So I'm going to draw it again. So H, 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 and H. And I said that this hydrogen, I'm going to replace it with Cl. Now, where does this hydrogen go? It's going to be joined. So I replaced it with this one. So it's going to join the other Cl, forming HCl. Let's take another example. Suppose I have C5H12. That's an alkane. And I added to it Br2. So there's heat and there's UV light. Again, one of those 12 hydrogens is going to be replaced with a Br. So instead of having 12, now I'm going to have 11. And one of those hydrogens is going to join the other Br. Note that this is Br2. So one of those Br is going to be here, and the other one, it's going to be here. So that was 1. 2, alkyl halide alcohol reaction. Now you need to know that in order to form alcohol or amines, I cannot do it directly from the alkane. So it's after the alkane turned into an alkyl halide, then I can continue and do a replacement, a substitution for the halogen, and replace it with nitrogen or replace it with OH. So for example, let's take this one over here. Okay? Or just a new example. CH3, but I'm gonna draw it in a simple way so that you can understand it. So here I have hydrogen, 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 and let's say I have Cl. I add to it a base. could be KOH, could be NaOH, LiOH, any base, any compound containing the hydroxyl group. Okay, so let's take this as a first example. What's gonna happen is that this one over here and this one over here will be replaced, switched. So what I'm gonna get is C, hydrogen, 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 and instead of Cl, now it is O. Now where does the Cl go? It's simply gonna join the K over here. And like this, I formed an alcohol from an alkyl halide by a substitution reaction. Let's take another example. Let's say you have Br, H, H, hydrogen, hydrogen, and hydrogen. And this was added to sodium hydroxide, something containing hydroxyl group. So the Br and the hydroxyl will be replaced. The hydroxyl and the Br will switch places. So we will get an alcohol over here, and this Br is gonna join the Na plus NaBr. Now the third type of substitution reaction is the reaction of switching an alkyl halide to turn into amine. So number 3, I have an alkyl halide. Let's take an example here of an alkyl halide having iodine. In order to make it an amino or amine, I need to get amine. This is called, it's ammonium, sorry. It's called ammonia. Okay? Now, what's gonna happen is the following. I'm gonna draw ammonia in this way. Okay? So, the iodine here and one of the H's, they join together to form HI, a compound. Now the rest, where does it go? This is the rest. It's gonna be attached over here. So what I will get is C, H, H, and NH2 with the 2 hydrogens, and here's the rest. Let's take another example. Suppose I have, I'll write it in a different way. C3H7Cl. Okay? Just like, I don't think I gave one. So C3H7Cl. Okay? That's an alkyl halide. Plus an H3. What's gonna happen? The Cl over here will be going with a hydrogen from over here. So HCl plus, now this NH3 lost a hydrogen. So it's gonna become NH2 attached to this C3H7. So let's move on and start topic 4.3. 4.3, in this one, you are going to be asked to compare aldehyde and ketones and to write the IUPAC name of aldehyde and ketones. Also to draw the aldehyde and ketone if the IUPAC name is given. You will be also responsible to explain the physical properties of aldehyde and ketones, like their polarity, boiling point, solubility, etc. And define what is a carboxylic acid and name it. There's no drawing. And draw the structure of carboxylic acid. So the only thing not included is to name or draw an ester. So let's begin. Compare and contrast aldehyde and ketones. Aldehyde and ketones, they both have the same functional group. So both have the same functional group called carbonyl. And it looks like this. Now this carbonyl, if it's in the middle of a chain, then I have a ketone. If it's on the side of the chain, at the end of the chain, I have an aldehyde. Okay? So, let's put it this way. It is an aldehyde, if carbonyl group is bonded or comes, it's much easier, if the carbonyl group is at the end of the carbon chain and there's a hydrogen on it. So if it's at the end, this must be hydrogen and this must be a carbon chain. Now, ketone, it would be a ketone if the carbonyl group is in the middle of the chain. So it's not on the side. So here's the double bond O, and I have, for example, CH3, CH2, CH3. Note that these groups, they don't have to be identical. It's just that I don't have hydrogens over here. Let's continue. Which of the following is a ketone? If I have a ketone, it would end with anone. If I have an aldehyde, it would end with anal. So this is butanal, that's an aldehyde, and that is a ketone. That's the name of ether, and this is how we name ester, which is not included. What is the name of the compound in the formula below? So again, we always choose the longest carbon chain. And this carbon chain is made up of 4 carbons, so it's a butane. Now, I have a double bond O, so the modifier or the suffix of this one, it's gonna be on. So butan, on. Butanon. Now, in a ketone, you always need to mention where is this butanon exactly. So you start counting from the side that is closer to the double bond O, and you will say 2-butanon. Draw aldehyde containing 3 carbon atoms. As I said, aldehyde, the carbonyl must be at the end. So if I only have 3 carbons, that's the first, that's the second, and that is the third. So that is a propanal. Next, describe the polarity of aldehyde and ketone. Now, since aldehyde and ketone both contain oxygen atoms, so both are polar. Now, if they are polar, then they can be soluble in water because water is polar and they are polar, so polar is always soluble in polar. So they can dissolve in water. Which of the 4 organic compound has its functional group below? So this one again is a carbonyl. They didn't ask me if this is aldehyde and ketone. They asked about the functional group. And this is also a carbonyl. Sorry, they asked about the organic compound. So as a functional group, they have the same functional group. But what's the name of the compound itself? This belongs to the family of aldehydes, and this belongs to the family of ketone, because here I have a carbon and here I have a carbon, whereas here I have a hydrogen. Now, Which organic compound acts as a proton donor? You will learn this in the next term. Proton donor means an acid. That's the definition of acid. So acid is a proton donor. And among all the functional groups and the family groups that we studied, carboxylic acid is an acid. So it is also known as a proton donor, because if I look at the structure of carboxylic acid, this acid can donate this hydrogen to another molecule or another compound. So that's why we call it a proton donor. Draw the structure of hexanoic acid. So we are dealing here with a carboxylic acid, and I have 6 carbon. Carboxylic acid, so it must end with COOH. So here's the carboxylic acid, and I have 6 carbons. So that's the first, 2, 3, 4, and 5. Don't ever forget the hydrogens. And that's it. All the best in your end of term exam.